Most things in physics have direction. Let's take a look at vectors and components and how we can work with those directions. This vector starts us here and ends us here. We could be going east and north in a sort of northeasterly direction, or we could be pulling up and to the right. Either way, the diagonal isn't always the friendliest thing to do math on. Sure, if you had a helicopter or a tank, you could drive from here to there, bulldozing people's lawns and going through their living rooms along the way. But most of us, when we go northeasterly, take the main drag, go east, and then turn left and go north. Either way, you get to the same place. These are called the components of the vector. You can go northeasterly, helicopter and all, or you can go east and then north, turn left on Kingston and be there just the same. Frankly, if you can go east and then north, you don't necessarily need the diagonal. If you have the two components of the vector, you can use them in any math instead of using the original vector. Let's give it a try. Let's find those components, the two legs of the right triangle that you can draw around every vector. To find the components, we're going to need a little bit of SOHCAHTOA. Here's angle theta. We know it already. It's given in the problem. This is Vx, the horizontal component, how far east we have to go. What side of the triangle is that relative to theta? Write it down in your notebook. Label opposite, adjacent, hypotenuse. Pause. Press play to check your answers. If we're after Vx is the adjacent. It's touching theta here. We know the hypotenuse. We want the adjacent. That sounds to me very much like cosine. Cosine is adjacent over hypotenuse. Aha! Multiply both sides by V in your notebook. Box your answer. It's the horizontal component of anything, anytime, anywhere, ever, as long as you have a nice little theta here measured from the x-axis. Pause. Press play to check your work. The horizontal component is V cosine theta. Whatever your vector magnitude is, times the cosine of the angle you're given. Now let's try the vertical component. This one is the opposite. See how it's directly opposite from theta? Check what you wrote down in your notebook a few seconds ago. Now find a nice little trig function that works with an opposite and a hypotenuse. Write it out, put in your values, pause, and press play to check your work. Sine theta is opposite over hypotenuse. Multiply both sides by V. Your horizontal component is V sine theta. Box those two. You can use them for the rest of your life, assuming you've measured this angle relative to the horizontal axis. First example, displacement. Displacement is how far you are now from where you started. It's the search and rescue problem. How far does the Coast Guard have to go to rescue an injured hiker? If you've got a helicopter, of course, you can fly the 5 miles northeasterly into the forest and pick up the hiker. No trouble at all. There's east, you want 30 degrees east of north. If, however, you need to drive or take any sort of vehicle, you need to take the roads. Vx, how far should you go east? Vy, how far should you go north? Draw them out in your notebook and find how far east and how far north you should go. Write your answer in bracket form when you're done. Pause. Press play to check your work. Make sure your calculator's in the right mode. Got it? Vx, 5 cosine 30. Vy, 5 sine 30. You're using the formulas you got before. That should give you about 4.33 miles east and about 2.5 miles north. So, drive 4.33 miles east, drive 2.5 miles north. If you want to write it in official bracket form, you can say, I intend to drive 4.33 miles east and 2.5 miles north. X, Y, horizontal, vertical, just like you did in math class. This is the same vector as 5 miles at east 30 degrees north. Next example, forces. Forces have components too. They have a magnitude and they have a direction. This athlete is stretching this yoga band with, let's say, 25 newtons worth of force at an angle of 120 degrees. See, it goes up, but it also goes back, not forward. See this angle? It is in the second quadrant. Let's see how far back and how far up she's stretching the yoga band. Find the components of this force. Pause, press play to check your work. Look at that beautiful second quadrant angle. That means we're going to be in for something different. Vx, 25 cosine 120, should give you negative 12.5 newtons. Why negative? Because x is forward, right, east, positive x-axis, and we clearly saw this yoga band was going backward. That negative is right where it should be. Why? No surprises there. 25 sine 120, that's 21.9 newtons of force up. As you can see from the picture, most of the force is up and very little of it is backward. You want to express this in bracket form? Go for it. 12.5 newtons backward, 21.7 newtons up. Same as the original vector we were given. Now, what if you have the components? You know your driving directions, but you want to see how far you're actually going. You go this far east and this far north. How far are you from where you started? Well, check it out. It's the tiniest little right triangle you ever did see, and we know how to work with right triangles. You can do Pythagorean theorem. X component, y component. Pythagorean theorem will give you the magnitude, or the number associated with your vector. Theta, well, let's see. We have the opposite. We have the adjacent. That sounds very much like a tangent to me. SOHCAHTOA it. Do we also have the hypotenuse? Of course we do. You solved for it yourself. But just in case you made a typo, just in case you kind of rounded funny, well, let's use what the problem gave us, because we know those numbers are right. Get rid of a tangent with an inverse tangent or an arctangent. The angle that the vector is going at will be the arctangent of the y component over the x component. Assuming, of course, the picture looks exactly like this in every particular. It's going north and east, up and to the right, and it never has the temerity to go into any other quadrant. Always check your picture. If you are in the second or the third quadrant, if you're going west and or south, check that picture because the calculator's arctangent and the angle on your picture will probably not be the same. For example, good old-fashioned 3, 4, 5 right triangle. You are flying into a very, very strong tailwind. There's a major air current. You want to hop on it and fly. Specifically, you're flying 3 meters per second west and 4 meters per second north. How fast are you actually going, tailwind, current, and all? Well, let's rearrange those vectors to make them look more like a proper right triangle. There is your velocity. You are going this fast in this direction. Let's see, Pythagorean theorem. 3 squared plus 4 squared, I know that one, it's 5 squared. You are going 5 meters per second. I have to assume that you are a bird or something, because any plane trying to go 5 meters per second is not going to be airborne. What about the direction? Well, the arctangent will tell you that the direction, according to your calculator, is negative 53.1 degrees. But this doesn't look like 53.1 degrees to me. Negative 53.1 degrees is like here. It's somewhere in the fourth quadrant. Negative 53.1, there it is. I'm not over there. Check the picture. This is a reference angle of 53.1 degrees. It's 53.1 degrees less than what you expected to be, which is 180. This angle here, the one you actually want, is 127 degrees, 180 minus 53.1. Again, check your picture every single time to see whether you have to add or subtract from 180 degrees. That's how you can assemble a regular vector in polar form with a magnitude and direction out of the two components. Now, you can find the components of a vector or use the components of a vector to do something interesting with. Take it away.